Good afternoon. Welcome to you get the dubious honor of being in the last DirectX session of the Build conference today. We're going to be talking about tuning your GPU usage for any form factor. My name is Dan McLaughlin. I'm the principal PM lead for Direct3D as a part of the Windows graphics team. I've been with Microsoft a little over 5 years, but I've been in the graphics industry for over 25. Started my career as a software programmer doing industrial animation and computer graphics modeling, then moved to Silicon Valley and did about 18 years in the computer graphics hardware companies, Ardent Computer and then Silicon Graphics, doing graphics hardware and software there before moving to Microsoft in 2006. 2006, I started as the dev lead for Direct3D 11 for Windows 7, and now I'm the PM lead for Direct3D for Windows 8. So today we're going to be talking about graphics hardware. We're going to talk a little bit about so we'll give you a sort of an agenda of what we're going to talk about. We're going to talk about graphics hardware and sort of the diversity you're going to see in the PC ecosystem for Windows 8. Then we're going to talk about a unified API system for being able to access that hardware directly. And then finally, we're going to talk about some tuning strategies for how to do that. I want to first start by saying that I'm going to make some assumptions about what you guys are thinking about in terms of we're going to be talking about DirectX. We're going to be talking about using C++ as the primary way to do that. So I'm going to make the assumption you've already decided that that's the path that you're going to be on. You should realize that even though that's true, Windows 8 has been built from the ground up to be hardware accelerated with the GPU. So a lot of the strategies we're going to talk about today are employed by the operating system to be able to take advantage of the graphics horsepower that's on the PC that's deployed. So when you leave here today, hopefully you'll have some ideas of how to structure your C++ DirectX code to be able to take advantage of the GPU resources that you find on that PC, and some strategies for how to go about tuning to get that best reach and to get that fast and fluid performance that you want to look for in your application. So first of all, I'm going to talk a little bit about graphics diversity, and I brought a couple machines with me that you're going to get a chance to see in action. I have here, this is a HP EliteBook 2740p, so it's a touch-enabled tablet convertible, so it both uses a tablet and a traditional laptop. This machine in the middle, the little one, is an HP Mini. This is a 5102T, so it's also touch-enabled. And has an Atom processor in it and a 3150 Intel GPU. And finally, I was going to bring a big gaming system, but they're really hard to get on the plane. So instead, I brought this Asus G73 gaming laptop, which has an AMD quad-core 5870. It's a 5870 GPU and an iCore 7 quad-core multi-threaded. So we'll get to see some comparisons about how each of those platforms runs and how we can get fast and fluid performance across that kind of range. So as all of you have already received, we have the tablet systems from Samsung. So this is a tablet form factor. This is running 10 graphics. The tablets like the HP, which is a convertible, also touch-enabled. Then we have sort of the traditional laptops, which are traditionally not have touch with them. Finally, sort of a new form factor that showed up in the last few years, which is the all-in-ones, which is a single chassis. Again, this one has touch-enabled as well. And then finally, high-end gaming systems, which are typically multiple monitors. So these are typical desktop, and we'll see what kinds of graphics are in each one of these. So given that we have, across the spectrum of Windows 8, probably the broadest scope of hardware that we've ever seen in the marketplace today, from highly mobile tablets and small form factors to very large gaming systems and high computational systems, which are using GPUs for GPU computationals. So how do we get access to that graphics horsepower? So I want to take a step back first and talk a little bit about DirectX versions and how we've sort of gotten to where we are in Windows 8. So if we go back to Windows XP, the hardware that was available at that time was DirectX 9 hardware. we worked very closely with our hardware partners and graphics vendors to be able to produce a specification for what was leading-edge graphics at the time. And Microsoft developed the Direct3D 9 API to be able to access that power of the GPU. And so there's a lot of technology out there today that's built and around DirectX 9, and you still see a lot of DirectX 9 hardware in the marketplace today. And we're actually going back and seeing that a lot of the more mobile devices are choosing to use 9 technologies. Then in Windows Vista, as the graphics technologies progressed and we worked on creating new and broader functionality for graphics, the DirectX 10 hardware specification was introduced. And to be able to get that full power of that GPU, Direct3D 10 was the way to do it. So if you had 9 hardware, you used DirectX 9. If you had 10 hardware, you used DirectX 10. Then in Windows 7, again, there was some major shifts in the graphics industry and sort of the technologies that were advanced. So we saw things like tessellation and compute that became available in 11. And so the 10 APIs weren't sufficient to be able to provide that kind of technology, access to that hardware. So we introduced the Direct3D 11 API. So that comes to the question of you as developers, well, what do we do to get access to all this hardware and not have to write 3 completely different code paths? And the answer here is, in Windows 8, we spent a lot of time thinking about how we make this much more easy for you as developers to be able to access the power of the GPU in a single API. And so in Windows 8, Direct3D 11.1 is our internal name, but I'm just going to talk about it from the sense of Direct3D 11 as sort of the overarching API set that we recommend that you use. And the way that we've done this is to use a set of feature levels which specify different classes of technology that are available to you as a developer, and so that you have a sort of a unified set. If you are running on feature level 9, that supports feature level 9 or DirectX 9 hardware and actually above. So each one of them is a proper superset of a subset of the previous one. So that says feature level 10 gives you access to 10 and above capabilities. Feature level 11 gives you all the capabilities from 9 through 11. So Direct3D 11, and I think one of the things that people get confused about is that when they hear that D3D 11 or Direct3D 11 is the thing that you need, that they confuse 11 hardware with 11 APIs. And 11 APIs give you access to hardware regardless of whether it's 9 hardware or 10 hardware or 11 hardware. And so you can tailor your application to use the 11 APIs regardless of the hardware that's actually on the PC that your customers are using. So 11 is the way that you want to be able to drive that graphics hardware, regardless of the hardware that it actually is. So let's talk about what's common across all of the feature levels within D3D. And we'll start with graphics hardware has internal processors that need to be programmed. So they're like little mini computers. Actually, they're pretty complicated mini computers. And they're parallel processors. And so HLSL is a language that we use, which is a C-like language, which allows you to program those computational units within the GPU. And that language is common across all feature levels. Similarly, we have both low and high precision integer and floating point operations that are available across all feature levels. And finally, there's a consistent implementation of the runtime and within the OS to be able to get advantage of this hardware. So now let's look at some of the things that you actually get from each of those hardware levels. Again, each of these builds, so you can look at the things that are in feature level 9 is across all hardware, whether it's 9 hardware, 10 hardware, or 11 hardware. So you have vertex shaders and pixel shaders. These are the computational units that do transformations on both the geometry level and the pixel level, and these run for each in parallel for each of those elements. Similarly, we have up to 8 textures that can be active at the same time, as well as multiple render targets. When we move to feature level 10, so that says that for anything that is feature level 10 or above, we'll be able to take advantage of additional shader stages. For instance, geometry shaders are only available at 10 and above. So if you want to have the broadest reach, then you have to think about where you're going to use geometry shaders and where you're not. Similarly, we have more textures that can actually be active, which gives you the ability to have much richer and more complex scenes. And a few other things, you'll notice that basic compute comes in here at 10, so this is an optional feature that's available on some hardware to be able to take advantage of the GPU computational horsepower as a more general CPU, or general computational unit. Then finally, when we look at 11, we get full computational power with full direct compute. This is required across all 11 hardware. So again, you'll see that as we move across the spectrum of graphics capabilities and feature sets, we get a much richer and more complex environment in which to build your applications. So how do we go about specifying what you want to be able to use? In D3D, what we allow you to do is to specify to the operating system the set of feature levels that you as your application wants to take advantage of. And this is in the order and preference of what you want to be able to use. So for instance here, in this example, D3D 11.1 or feature level 11.1 would be my preferred feature level. But if that's not available, then use 11. And if that's not available, use 10.1. And then if that's not available, use 10. So, and I intentionally took out 9.2, which is also a feature level here, to show you that you don't have to specify all of them. In that case, then, it would say, oh, if the hardware supports 9.2, but I don't really care about 9.2, so it's going to step back to 9.1 instead and give me the capabilities of 9.1. Then what we're going to do after we've created this list is we're actually going to make a D3D call, which is the D3D 11 create device. And this is where we're going to specify the feature levels that we're actually interested in. And what the operating system is going to do is it's going to return in this variable the feature level that's actually available on the system. This then allows you to be able to configure your software to be able to configure based on the feature level of the hardware that you're actually running on. Because remember, in this PC ecosystem, you may be designing on one piece of hardware, but your customers are going to have a very broad range of hardware that they're going to have at their disposal, right? So one person might be running on feature level 9, another person may have a high-end laptop like the Asus, right, which is running 11. So you need to be able to configure your software so you get that broadest reach and can hit those customers no matter what platform they're actually running on. So how do we do that, right? What's the way that we actually go about tuning to get that broadest reach? So what I want to do now is show you one application which is going to run across all three of these systems up here. And it's actually running exactly the same code, all three of them. And the code is actually going to do some dynamic tuning, actually going to do a little bit of benchmarking at the very beginning to be able to try to figure out what performance level it actually has. So let's start with, we're going to start here in the middle. So this is a 10 device, and this is a particle system demo. And what it's actually doing here is it's, you notice up here in the top, there's a frame counter so we're getting about 59, 60 frames a second here. And we can interact with this particle system. And so the code that's running here, each particle is actually being transformed on the GPU. So I think there's looks like about 940 particles that are running on the screen at the moment. And each one is getting transformed, and then we're actually using the geometry shader, which is a feature level 10 construct, to be able to actually take those points and convert them into two triangles and a triangle strip for each one, and then render a textured quad for each point. And see, I can interact with them, and we're getting very fluid motion here. This is also touch, so I can it's basically repelling the points as we move across there. So now we're going to move to the second machine. This is a 9 device, and as you might remember from what I said earlier, feature level 9 doesn't actually have geometry shaders, so we actually had to build a second code path to be able to generate the pixels in the same way that we did before. Here, again, this is a little bit lower powered machine. And you notice it's having a little bit of problems getting up to 60 frames a second here today for some reason. I can usually get it to 60. Let's see if it can get there. But it's actually doing some dynamic, there it goes. Well, it was almost there. But notice we're still getting fluid motion, but now we've scaled back the number of particles that we're actually generating. Again, what we're doing here is we did some dynamic profiling at the very beginning to determine, because we know in this particular case that the performance that we're getting is really directly proportional to the number of particles that we're actually trying to draw on the screen. Okay, so now let's move to our third laptop here. Now this is a high-end gaming system. It's a DX11 card, and you'll see a little bit of difference in terms of performance of what we get here. Notice that it's still computing, and it found that it tried at 20, and it's now up to 50,000 particles, and it's hitting 60 frames a second with no problem whatsoever. So you can see that with the same code, we're able to get a much richer experience because we can draw more particles on the screen in each frame. But regardless of whether we're running on 10, 9, or 11, we were able to give it a similar experience, right? And get a frame rate that all felt very fluid and fast and fluid, regardless of the number of particles. So this is an example of how we can take advantage of the horsepower that's there on the GPU for the particular system and be actually able to tailor our applications such that regardless of the particular feature level or regardless of the performance level, we can get a smooth and fluid motion. It's a little bit mesmerizing, isn't it? All right, let's go back to the slide. So let's talk a little bit about a strategy for how you go about getting that broadest reach and take advantage of the GPU horsepower that's there. First of all, my recommendation is that you start with 11 hardware. And the reason for doing that is that because if you remember that list of feature levels that we talked about a little bit ago in the code sample, the runtime is set up to be able to allow you to be able to pick the feature level that you want to try at. And so if you have a feature level 11 hardware, that means that you can then dial it back and actually be able to play with and sort of tune your applications to be able to run on each of those different feature levels. So even on like my 10 laptop, I can change that feature level to be 9 and then actually make sure that the code is actually running on feature level 9 as well. The next thing to do is really think about if you want that broadest reach. We know that as we look at the PCs that are going to be available, that are available in the marketplace today, and where we expect them to be across the Windows 8 deployments, we expect that feature level 9.3 is going to be probably the most prevalent feature level. That's the base level that will be there. We do know that there are a bunch of 9.1 parts that will probably be a part of the upgrade paths and upgrade scenarios for people who already have laptops and PCs in the marketplace. So I think it's important for you to think about and actually for that broadest reach to target feature level 9 and then be able to scale up and take advantage of the hardware that's there if there's additional horsepower that's there. So as you see, we were able to actually show that same application running across all 3 feature levels. The next thing that I think is important for you to think about is how do you go about profiling or benchmarking at runtime when your application is already deployed for your customer system about what the performance level really is. So once you've done that kind of those quick set of frames, and in a Metro style app, you have that splash screen that comes up for the very beginning. If you can also put another splash screen up, which will give you the opportunity to be able to do a few frames in the background before you actually get your application up and running. Finally, beware of the differences. As I mentioned, feature level 9 doesn't have geometry shaders. Feature level 10 doesn't have tessellation shaders. So if you want to take advantage of those things, you can write an application which requires those features, but it also says that you're going to limit the scope of the broadest reach that you're going to have in terms of the customer base that you can touch. So finally, test against the feature levels. Be able to dial down and make sure that your code actually runs against feature level 9, feature level 10, and feature level 11. It's not sufficient, though, to do it that just on one machine with changing your feature levels. It's also highly recommended that you test across multiple PCs that actually have those particular feature levels. At least pick some that have some different performance characteristics so you can actually benchmark your code and be able to figure out whether the benchmarking code that you think is running is actually doing what you want across those architectures. So if you start with feature level 9, then let's talk about how some ways that you can differentiate your application. You can make your app pop when those additional features are available. So one of the things that we've added in Windows 8 is actually Stereo 3D. And if you were downstairs in the booth, you actually saw that we have a TV set up downstairs, which is a stereo TV that was actually connected to a system that was doing stereo. All of your Samsung tablets actually are capable of stereo, so I don't know whether you knew that or not, but if you plug in an HDMI 1.4 cable to your tablet, you can actually get these images were actually taken from one of the Samsung tablets. So in stereo, the way that we do stereo is we actually generate, so we've built into the OS the ability to be able to drive stereo regardless of the kind of technology that's actually in the screen to be able to do that stereo capability. So all you have to do is be able to render a left and right eye, and you do that by generating that to a swap chain, by a swap chain that has, that's an arrayed swap chain. So you have a left and right eye, and you can just draw to those, and then the hardware actually will composite those into the combined image. So next thing is on feature level 11, there's tessellation, which will allow you to get higher resolution geometry. There's a talk back in 2008 that Alison Klein did that was from PDC 2008 that talks a lot more about tessellation. So highly recommend you take a look at that if you're interested in more details on tessellation. Finally, from a standpoint of how you increase visual quality, one of the things that look at as you look across feature levels and across performance levels is to look at the visual quality you can get from higher resolution textures. So these two images, and hopefully you can see the differences. The image on the left actually has 8 times the resolution in the textures as the same image, which is on the right. This comes from a sample that was in the DirectX SDK, which from June 2010, and all we did was to reduce the texture sizes there to generate those two images. But you can see how by adding more texture complexity or texture fidelity, you can see the additional quality around the wheels or in the sand at the bottom. So finally, one of the ways to think about this from a quality versus performance standpoint, if you went to Chaz's talk, which is on Wednesday afternoon about MIPMAP levels and the Direct3D pipeline, MIPMAP levels are a way that we can have successively refined smaller versions of the same image, which allows the hardware to be able to do better filtering and to do texturing. What that also says is that on platforms that have lower performance or have less capabilities in terms of the amount of geometry, the amount of data that's available on the GPU, we can actually say that we're only going to load the first few levels instead and not use that top level MIPMAP, which will give us better performance, but at the cost of visual quality. So another thing to consider when you're looking at how to get that broadest reach is also to think about how you can do the same kind of things with your geometry that you can do with your textures. And that says, if you have a representation of a model which is highly complex, if you generate also lower complexity models of the same thing, there's 2 ways that you can use that. When it's far away in the scene, then you can use that reduced size model, right, less vertices, which will take less computational power in the GPU to be able to render it, and also allows you to be able to step back on hardware that doesn't have as much performance from the GPU, from the vertex processing perspective. Also, multi-sampling is one of those things that gives you much better visual quality, but it does come at a cost. One of the ways to do that is if you know that your application is pixel bound, which means that the thing that's blocking you from getting to that frame rate is the number of pixels you're trying to draw on the screen, you can dial back on the multi-sampling that you do for anti-aliasing. This will come at a cost for visual quality, but if you're trying to get that fluid motion, then that's one of the ways to do it. Finally, a third way to be able to do this is, if all else fails, you can actually generate a render target which is smaller than the final frame size, and then be able to scale up at the very end. One of our samples that's available in the sample gallery, which is a post-processing sample, uses the same technique where we actually reduce the size of the image that we're actually doing the post-processing on and then scale up at the end. So if you're looking for code samples of how to do that, that's a place to go look. One of the things to be careful when you do this is don't do it with text, especially if you're doing smaller scale factors, so you're only scaling back by 10 or 20%. If you try to do this with text, it looks really bad. So the recommendation here, if you're going to mix 2D and 3D, is do the 3D stuff and do that at the reduced resolution, then scale up at the end, and then draw your text or your HUD on top of it at full resolution. That's the best way to get really high quality text. So one of the things that you have to be really careful of is that feature levels don't equal performance. We used to think that this was true, and generally it is that each successive generation of hardware gets faster and more capable. But as we're seeing, as we're moving to a broader range of form factors, that's not always necessarily true. So you could have a lower performance, more fully featured graphics device that happens to be deployed. So one of the things that you have to do is make sure that you're actually at your runtime checking to see what the performance is. Don't make the assumption that it's just because it's feature level 11 that it's going to be something like the Asus over here, which has got really high performance. So we used to think the curve kind of looked like this. And the scale is arbitrary because it's more to give you a sense of what each successive generation has done in terms of the feature set and the size. And so we used to think that the curve looked a lot like this. What we've really found is it looks more like this. Is that, yes, the high end of each of those feature levels is progressing as we grow over time. But the other thing that we're finding is that designers are making different trade-offs in terms of they want to provide the feature set, but they also want to be able to do that in a low power envelope. And so what they'll do is make trade-offs in terms of, especially across that feature set. One of the interesting things to do is all of these laptops happen to be plugged into power right now. If I disconnected the power and they were running on battery, you'd notice that the performance envelopes are going to look very different. That 50,000 particles on the Asus is going to drop to about 10,000 particles, right? So we're going to drop a factor of 5 just because we're running on battery, and because the laptop is now doing things to be able to take advantage of to reduce its power consumption, so you get better battery life. Now, battery life on that particular device is not exactly what it was designed for in the first place, so you usually get about an hour and a half on that one. So how do we go about doing profiling? So let's talk briefly about how we do that. First of all, we want to create the device, which is as we saw in that code sample, then gives us the ability to find out what actually we have on what hardware we're actually running on. Then, based on that feature level that comes back, set the sort of the coarse grain limits on what you expect to be able to do. Choose the code paths that make the most sense for that feature level. Then render a set of characteristic frames, and I'm going to show you some code about how to do that. And then adjust the way that you're going to do your coding based on those results that come back at runtime. So here's a piece of profiling code we're going to walk through. First of all, one of the things to remember is that the way that the runtime works within the operating system is we have code that runs on the CPU and we have code that runs on the GPU. And we intentionally overlap those. And so for us to be able to get accurate timings, we actually need to make sure that all the work that's been done on the GPU is done before you get your profile results back. Otherwise, you're going to not get valid results. So what we're going to use is a query event, and this is actually going to allow us then to be able to determine that all the work on the GPU has been completed. So we're going to create that first. Then what we're going to do is we're going to flush to make sure that the pipeline's clear, and then we're going to render a set of successive frames. Now notice I didn't present here, and that was intentional. One of the things that you have to be careful of is if you actually are doing profiling while you're running and you're actually displaying to the screen, that refresh rate is going to be locked to the refresh rate of the display, which says if your application can run at 120 frames a second, you're going to be still locked to the refresh rate of the screen, so you're not going to be able to get advantage of the full computational power that you have available. So by doing this and rendering off-screen and then flushing, the flush is also important. And the reason it's important is because otherwise, it could be that all your commands get buffered up into one big buffer, and then at the very end get sent to the GPU, and that's not going to also be representative of the way that your application is actually going to be running when it's actually deployed. So be careful of those kinds of things. Make sure that you're actually characterizing the performance of your application as it will actually be running rather than arbitrarily. So the key thing here is you want to render a set of representative frames to give you an idea based on what your application is going to do, whether it's geometry limited, whether it's fill limited, whether it's a combination of how the characteristics of balance goes between the CPU and GPU. So one of the things you want to think about is what is in that actually render code. That render code actually should represent sort of the full dynamics of your system so that you get a sense of how the performance is working between the CPU and the GPU as well. So after we've rendered those frames, then we're going to say end query, which that end query then says, make sure that that round trip has happened through the GPU, and we're going to wait until the runtime says, yep, I'm finished, right? Everything's happened on the GPU, and then only at that time do we actually get back the timers to tell us how long it took to render those characteristic frames. So this is the code that we're actually using in the particle system demo. We're using 18 frames because that equates to about 0.3 of a second in terms of if I want to hit 60 frames a second. Probably one of the other things you want to think about is that you want to give yourself a little bit of buffer. So at 16 milliseconds for 60 frames a second, you want to have a little bit of overhead to be able to say what happens if there's some little glitchy things. Maybe you get some highly complex scenes, and so you don't drop back to 30 frames a second sometimes. Because you're going to remember, it's not like you just drop from 60 to 59. You're going to miss a frame. You're going to drop from 60 to 30. And so that's going to be pretty obvious, especially if you want to try to maintain fluid dynamics or something that's going to be very fluid. And especially if you're doing game dynamics or you're doing something that has a lot of interactivity to it, that flipping back and forth between 60 and 30 is really going to mess with people's heads. So the goal really is to get to 60 frames a second. And as I mentioned earlier, power is one of those things that's really very closely related to getting to that frame time. And there's a couple ways that you can do that. So let's talk about how we can actually hit those goals. And one of the things to do is look at the rendering costs in general of how do I minimize the amount of complexity that I have in my shaders. How do I minimize the amount of redundant work? So if you look at the loops that you're actually performing, how can I pull the things that are out that are constant across that loop, pull it outside the loop so that you're doing less work within the inner loops? There's sort of two cases that you run into. One is where you have your geometry limited, which means you have a large amount of geometry that you're processing on an individual basis, and so if you have high overhead in terms of the amount of computation that you're doing at each vertex, then look at the performance in particular around the geometry side. Often what we find is that mostly the bottlenecks are on the pixel side, because that's where you actually have the most expansion of data. And so look at the rasterization piece in particular to look at ways that you can actually reduce the amount of depth complexity that you have. When we think about depth complexity or overdraw, that's actually the number of times that an individual pixel across the screen is going to get drawn to generate that final image. And so one of the things you want to do is look at how you can reduce the overall overdraw, or the amount of times that you're going to touch the same pixel. And think about that from an average across the overall screen. So to do that, we've actually we have some new things that we've added to Windows 8 that are available across all the feature levels to help reduce on this power consumption, and also to help us to get to those performance levels. So the two things that I'm going to talk about today are minimum precision and some tile-based rendering things, and I'll get to what that means in a minute. So minimum precision. So when you think about what happens in the GPU, if I have this whole set of cores which are replicated across the part to be able to do in parallel all those computations, All those computations are today done in 32 bits per pixel, or 32 bits per computation. What that means is that there's probably a lot more than 32 register or 32 bits of register to be able to do those computations. In some architectures, it's actually possible that those have been done in a way that's vectorizable, and they actually can split them into 16 bits at a time. And so what we've added is the ability to be able to give hints to the operating system that the computations that you're doing actually can be done in less precision. So this takes some analysis on your part to be able to figure out whether you actually can get away with using 16-bit integers or whether you can get away with 16-bit floating point. Because there are some characteristics that happen that if the precision isn't enough, you'll either get jaggies or you'll get things that jump around, or there won't be the smoothness you expect. So you're going to need to do some numerical analysis to make sure that you can actually get away with the lower precision. But if you can, then what you can do is in your code, and especially in your HLSL code, you can actually specify that it's okay to step back to a minimum precision, which is less than 32 bits. And that says on architectures that do have the ability to be able to say, I can split this and I can actually run twice as many operations in the same amount of time. Again, one of our goals is to be able to reduce the amount of time that we're running at a high power state so that we can actually get better battery efficiency, right? So if I can run the same amount of code in half the time, I'm either going to get better performance or I'm going to reduce power consumption. So depending on which one you want to go, but they're both kind of very closely related. So what we can do is we can actually give hints to the operating system to say it's okay to be able to step back and use those lower precision operations. So here's an example. Again, this is from the 3D post-processing sample that's available in the code gallery. And this code is actually doing downscaling 3D brightness paths. The details of exactly what it's doing are not important to what I'm trying to point out here, but you'll notice that there's a set of floating point things that are declared within the shader. And all of these, because they're called floats, are actually 32 bits in value. And so what we want to do is be able to say it's okay to be able to use 16-bit precision to actually do this same computation. So what we're going to do is we're going to change each of those to notice that now we've declared them to be min16. That says that if the hardware is capable of doing it, it will actually be able to use those minimum precision operations and actually get better performance. Now, one of the things I want to also point out is that notice this last return value we didn't change. And the reason that we didn't do that is one of the things that as we thought through how do we make this available and how do we reduce the complexity for you as developers is if we said, well, the data that comes in could be 32 bits or it could be 16 bits and it could be changing, then how do you keep track of that? Because you're not sure exactly which things are going to be happening when. So what happens is that all the computations that happen within the shader actually can be reduced performance or reduced precision. But it still says that the data that comes through each of the stages is still going to stay at the resolution that it was to begin with. What that means is that you don't have to worry about the complexity about am I going to be on a piece of hardware that does minimum precision or not, and do I have to do something different? So we're going to take care of all of that for you and make sure that the computations that happen, which are the place where we can actually get the best benefit from this, actually happen without having to deal with a lot of data conversion. So now let's talk a little bit about one of the new architectures that's been showing up more and more as we think about power consumption and how do we be able to get better power utilization and get less area within chips to be able to get the same kind of performance but actually take less power and less area. And so one of the ways to do that is to actually do what we call tile-based rendering, which means that I have a cache. So if you think back to the way a GPU actually works, the GPU has to be able to access all the pixels that are available on the screen at a very high bandwidth to be able to draw those and do those in parallel. So when the pixel shader runs, to be able to run in parallel, it's got to be able to access memory, both to be able to read things and write things out in a parallel fashion. And that can be very, very expensive, both from a silicon area standpoint and from a power standpoint. So one of the ways to do that is to actually build a cache, which is faster, which has a smaller area than the full size of the screen. And then the goal then is to keep everything in that cache as long as possible When you're done with those operations, then write it out to the screen, the area that's going to be displayed on the screen, and then go do it again for the next tile. So let me give you an example. So in sort of a typical rendering fashion, you would generate a set of commands, and those set of commands go to the GPU, and the picture gets generated. On a tile-based rendering system, you send those same set of commands, and what's going to happen is I'm going to execute each one of those tiles, that same set of commands, over and over and over again in succession. Once that's done, then we're going to push the final image off to the screen. So you can see how, while you've done the same thing, the GPU is actually going to take advantage of that tile to try to keep things in the tile and in the cache for a longer period of time. But it does say that it's going to have to execute those commands multiple times. So there's some challenges with that from the runtime perspective and from an overall GPU utilization perspective. And the challenge is that sometimes, depending on how you write your code, we have to create multiple copies of the data to make sure that we can actually execute those buffers multiple times. Because otherwise, what you get is wrong rendering and wrong pictures on the screen, and that's not good, right? So what that also means is for us to make sure that in the operating system that the data is correct, we may have to make copies of the data to ensure that the rendering, when it's duplicated, actually does the right thing. So the solution around this is that we've actually in Windows 7, there were a set of APIs that did partially for this. And I'm going to show you an example of how that works in just a minute. But we've expanded that within Windows 8 to be able to do this in a much more general way, to be able to take advantage of a lot more scenarios that makes the tile-based rendering a lot more efficient. So, but to use these hints, you are making a promise, right? You're making a promise about how your rendering code is going to work, because when you give us that hint that says we're not going to make those copies, and then if you break that promise, the rendering is going to look wrong. So don't just go arbitrarily say, oh yeah, I'm going to use these, and drop the hints into your code without thinking through, am I really following, am I really doing what I say I'm doing in terms of what these hints mean? Because if you break that promise, the render's not going to be what you want. So a couple tricks here in terms of what you want to do. One of the things to think about is you want to avoid mid-scene flushes. That means you want to make sure that everything that you need to do can be done in a successive fashion such that you don't cause the pipeline to have to be completely fleshed out because there's data over here that I can't do anything about it until it's completed for all of the tiles. Right? That requires me to flush the whole thing, make sure everything's done, then make the copy, then do it again, and do it again, right? The other thing that can cause this kind of pattern is to swap back and forth between the render targets that you're actually using. So think about, I have an off-screen render target, and I have the render target which is tied to my back buffer, which is going to go actually out to the screen. Now, one of the ways to do that is that I'm going to go render over here, and then I'm going to go back to my main render target, and I'm going to draw something with it. Then I'm going to go over here and use this as scratch space, and then I'm going to go back to my render target, right? So I'm going to kind of do this back and forth thing. That's really bad, because each time you go back to that main render target, you've just caused a full flush. So what you want to do is go do all that off-screen rendering stuff first, use that render target completely, and then use it. Right? So think about the ways that you can make sure that you're efficiently using those things. Sometimes when we build object-oriented code, we do things that make sense from the object standpoint, but when they actually go execute on the GPU, we do a lot of thrashing stuff. So be careful of the way you structure your code such that you don't do that and say, oh, well, this thing is going to go off and render over here, and then it's going to come back. Right? So it may mean that you need to think about the way that you structure your rendering loop such that you get efficiency of using those resources in a way that allows us to take advantage of those and get the best performance that you can. So also, when you're using textures, one of the ways that when you're thinking about things like, let's say you have a large texture that you're using in a flyover, so and you know that the user the user can't actually jump way ahead, so you're going to page in along the way. So I'm flying in this direction, so the area that's out there I don't need yet. And so in the background, I can start paging that in because I know that the direction the plane's flying is that way, and so I need the terrain in 10 or 15 frames. So one of the ways we do that is we keep a big texture, and we kind of reuse it and push things into it, because you don't want to be creating textures on the fly. That can be kind of expensive. But what we can do is preload the things in the area that we know where we're going. So again, this is one of those cases where if you do it naively, we're going to have to make a copy because we don't know you're not going to use that area when we go render the triangles in the current scene that we're doing. So one of the ways to do that is to actually use scissors. And so you can say, well, I know I'm just going to go draw in that area out here, so I'm going to scissor into that area so that this is the only area I'm going to use. Then that gives us and the operating system the hints to know, okay, the rest of this space, and if you're not referencing it, great. I don't have to make copies, and I don't have to keep track of that. The other thing that's here is discard and override. So when you have resources that are on the GPU, you're going to map those resources so you can actually write to them on the CPU. So when you map them, you can actually give hints to us, to the operating system, to say, the stuff that was in there before, I don't care about. Right? Which is what discard means, right? Throw it away, it doesn't matter, I don't need it again. I'm going to map it and I'm going to write over it completely. The other is to say, no overwrite. So I'm going to map it, there's data there already. I make the promise that the stuff that's there that you're using for other things isn't changing. So I'm going to write here in this other section, it's okay. I haven't changed anything back here. And so, therefore, then, again, we don't have to make copies, and that gives us a lot more efficiency in terms of how do we go about making sure that we're doing the right things. All these things, whether you're on a tile-based rendering system or not, are good things to think about because they are ways that you can be much more efficient in terms of the way that you use the resources of the GPU and the way that we're doing handshaking between the CPU resources and the GPU resources. So regardless of the underlying GPU architecture, these kinds of things are actually important to be thinking about in your application if you really want to get the best performance and get that broad reach. So one of the other things that we've added as a part of Windows 8 is, again, this concept of discard on the render target in particular. And this ties back to, you probably saw a very similar piece of code in Chaz's talk on Wednesday afternoon, which is basically doing the same thing, right? After we present, if your application is full screen and you know that you're going to replace every pixel on the screen anyway, then just tell the operating system, I don't care about the image that was there before. Now, if you're using some of the other new things that are available in Windows 8, things like clipping rectangles to be able to say, I'm only updating a certain area or I want to be doing scrolling, don't do this, right? Because what we're actually going to do is we're going to keep track of those things and only update the areas that are important. So if you're doing like a flashing cursor and you're only going to change something in one area, don't discard. But if you know that your application is going to be generating all the pixels anyway, then go ahead and tell the operating system that I'm done with that, right? Then we can be more efficient in our usage of the resources there. So let me give you an example, and this dynamic geometry example is actually also available on Windows 7. So this is not new capability, but the extension of that to 2D textures is. So let's think of an example where, let's say I'm in a game and I've got a window which I'm going to represent as two triangles, right? So it's basically a quad, and I'm going to draw it as two triangles, and it's got some transparency to it. And let's say that somebody throws a ball at it, and the instant that the ball hits the window, those two triangles no longer are valid for me to be able to represent what's going to happen in the next frame, right? So what I want to do is I'm going to have a buffer that I'm going to create. So I'm going to create a vertex buffer that I'm going to use for these kinds of dynamic events. So because that window may never get broken, right? In which case, I don't really need to generate those triangles until the point at which that happens. So I have this scratch buffer, basically a vertex buffer, that's on the GPU that I'm going to use for these kinds of events. And let's say the ball hits the window, right? And the instant that the ball hits the window, in my physics code, I'm going to go generate that geometry, right? And then I'm going to use that to draw the frame, right? Because all those shards of glass are going everywhere, right? And so we need a lot of different triangles. Now later on in that same scene, right? Again, I'm walking through my data structure and I say, oh, I've got another one of those, right? So here, I'm using that same scratch space because it's a big buffer and I only needed part of it for that first one, and I'm going to use it again, right? So this is a sequence where we'd have to make a copy because we don't know that the data that was from that first one isn't getting changed by the second one. But if we do the map, when we do the map calls, if instead we say at the beginning, discard, right? All the data that was in that vertex buffer before, don't care, right? Not important. But then the second one's like, keep that first part around. I promise, right? Here's one of those promises again. I promise I'm not touching the first part, which means that draw call that we've already got queued up that may or may not have been finished yet. And if we're doing a tile-based rendering, then we're going to have to do it multiple times, right? It's okay. I'm not touching that. You don't have to make a copy of it. You can keep it rather than replicating it 6 or 8 times or 20 times, depending on how many tiles you're actually going to do, right? So these are the kinds of hints that we can do on the map calls to be able to allow us to take better advantage of the GPU resources that are there. Similarly, the same kinds of things you can do now with Windows 8 when you think about textures. So if you're doing something like atlasing and you're changing particular pieces in the atlas because the character is being damaged or something's happening that you need to change that particular piece, you can use scissors to be able to change that piece, and then also use the overwrite and the no overwrite if you know that the piece that you're changing isn't actually being used in the rendering that's happening in the current frame, right? Again, that gives the operating system the ability to reduce the number of copies that we have to do and get better performance for you and your application. So let's recap. Where are we? We've gone through a lot of stuff here, right? So Windows 8 has probably the broadest scope of hardware that we've ever seen in terms of the diversity of GPUs and the diversity of form factors. And so we've designed from the ground up, from the very beginning of Windows 8, to be graphics hardware accelerated. A lot of these techniques that we've shown you today, we're using in the operating system to be able to get the performance at all different levels within the operating system. We've really designed to be able to take advantage of the hardware that's there, and we really tailor the experience so that we can actually run on 9 hardware and 10 hardware and 11 hardware and take advantage of the GPU horsepower that's there. Secondly, D3D11 is the API for you to be able to access the GPU resources, regardless of the hardware that's actually there. So break that connection that we've had for a long time about hardware equals runtime. The D3D11 APIs are the way to get access to the graphics hardware, regardless of the hardware that's actually on the system. So you really can get the broadest reach for the PCs that are going to be in the marketplace and that are already available today, and hit those markets. And when you can do that, then that says that the amount of the customers that you can touch with your application is going to be that much broader. So what do you need to do? Your call to action as developers. First of all, really design for 9, right? If you really want to hit the broadest reach, design for 9. Adjust the runtime based on the feature level that you find at runtime. Take advantage of the things that are there. So differentiate your application by taking advantage of the features that are there for higher level feature levels, but don't depend on them if you really want the highest reach. So if it's there, so think about stereo. Stereo is available not on just high-end hardware anymore, right? Your tablets that each one of you have, you can go home and plug that into your stereo TV and actually get stereo today. We actually have stereo samples that are available on the gallery where you can actually go and play with that. So take advantage of those things. Also, take advantage of the things that are in Windows 8 that allow you to get better performance by using minimum precision where it makes sense, and take advantage of the tile-based rendering optimizations. Those work across the board, regardless of whether the architecture has a tile-based architecture or not. Finally, as I'm the last graphics talk for the day, all of these have already happened, but they're all on video, so I'd highly recommend that you go back and take a look at these. There's some great talks here. All of these will give you some more insight and better ideas about how to take advantage of the DirectX graphics stack. Finally, these slides are also going to be available online, so these are actually direct links to documentation that's available for Windows 8 around the 11.1 feature set that's available in Windows 8, as well as some resources that are already available that have been available for a while in terms of feature level things. And the talk that I mentioned earlier that Alison Klein did in 2008 on the GPU and taking advantage of those high-end features is also available. So I'd highly recommend that you take a look at that. Finally, thank you very much. This has been helpful for you all. If Thank you. We'll be following the forums, so if you have questions, I'll be up here afterwards, so you can come up and ask questions. Also, feel free to contact us through the forums, and please also fill out the session feedback if you would. Thank you very much.